Cosmology and astrophysics. So we were discussing in the last session how to find the distance between the distance of the planets, stars, and galaxies. For this, we can use Kepler's law, we can use Hubble's law, we can use radio detection, like using a radars or radio telescope, or we can use a trigonometric parallax. There, there are units in astrophysics which, because the distance between the stars, the distance of the planets, it's in terms of meter, it's too big. So we use different units or equivalent units. So we can use astronomical unit. We can use astronomical unit. We can use light year. We can use parsec. You should learn, memorize the equivalent. Like example, if we say one astronomical unit, so one astronomical unit is equivalent to 1.5 into 10 to the power minus 10 to the power 11 meter, not minus by mistake. So it is equals to 1.5 into 10 to the power 11 meters. So 1 AU, astronomical unit, we can write as AU, is equals to 1.5 into 10 to the power. Yeah, that's right. Actually, one astronomical unit is also a distance between the Earth and the Sun. That's true, Faris. I will relate this astronomical unit, like why we call this a. So that is equivalent to 1.5 into 10 to the power 11 meter. Then we have light year. Light year is also, it's a distance traveled by light if it travel for 1 year. So in terms of meter, one light year is approximately equal to 9.46 into 10 to the power 15 meter. It is for 15, sorry. I type 14 here. And one parsec, that is equivalent to 3 into 10 to the power 16 of the meter. Exact value is 3.08, but you can write like 3.1 or 3.1 into 10 to the power 16. That is one parsec. The astronomical, in terms of astrophysics, we use these parsec. So one parsec is just denoted by PC. And for light year, we use LY. LYR is abbreviation, but normally LY is there. And one parsec is denoted by PC, which is equivalent to 3.08 into 10 to the power 16 meter. Meter here is a unit. Then the comparison between astronomical unit, light year, and parsec. So one parsec is equals to 3.26 light years. And same, if we have light year in astronomical, this parsec in astronomical unit, that is 1 parsec is equals to 206,265 astronomical unit. So these are the comparison of the units in astrophysics. So we can use different laws to find the distance. We can use it to find the time period. But before this discussion, uh, for a star, so what we consider the star, we consider stars as a perfect black body. This is our assumption. So we consider stars as a black body. So when we consider a star to be a black body, so we can apply the black body's laws. So there are two laws. One is the Stephen Boltzmann law, and another one is a Wien's displacement law. Basically, the term black body means a body which can absorb all the radiation will fall on it and can release those radiation. We call that as a black body. So if we sketch a graph for a black body, like example, if you're sketching a graph for energy and the number of the particle, or it can be in terms of wavelength as well. A perfect black body emit all the radiation which it absorbs. So if we have on x-axis, if we are taking a wavelength, and on y-axis we can take radiation flux or intensity. We can also say radiation intensity. The term radiation intensity means how much energy uh, in per unit area in 1 second. So example, here we have an intensity, or it can be a luminosity as well. So basically what happened, the particles, if you have any material at a certain temperature, so and it is made up of particles, some of the particles are moving very fast, some of the particles are moving very slow, but most of them are moving with the average speed. Like most of them have average. So when we sketch a graph, a black body, a graph for a black body, when we represent this, so this is the shape of this graph. What this shape of the graph shows, it shows like how the variation is there for distribution of energy in terms of wavelength. You can see some of, like it is emitting out energy, like some are longer wavelength, it is emitting out longer wavelength, also it is emitting out shorter wavelength, but most of them are average wavelengths. So if most of them are average wavelength, if we increase the temperature, as we increase the temperature, we know the formula E is equals to Hc over lambda. As we increase the temperature, so energy will increase. If the energy will increase, the wavelength or the wavelength at which the maximum intensity is there, that will become or change to shorter side. So as the object will become hotter, as the temperature of the object is increased, what we'll observe the peak will shift towards the left hand side. As it become hotter, the peak is shifted towards left hand side. So this one is at low temperature, this one is at moderate temperature, and this one is at high temperature. These are the black body graphs. Is it clear? The black body graphs first. The black body graphs. So this black body graph explain the relation between the wavelength and the temperature according to Wien's displacement. As you can see, if I increase the temperature, if we increase the temperature, the energy increases and the wavelength becomes shorter. So as the wavelength will become shorter, what will happen? If we can simply say that temperature and the wavelength, or the temperature and the energy here, are inversely proportional to each other. So when two quantities are inversely proportional, the first law is the Wien's displacement law. So according to this Wien's law, temperature, but it should be in Kelvin, is inversely proportional to wavelength. And when two quantities are inversely proportional, what we do, we replace this proportionality sign with equal to and constant. So we can say k is a proportionality constant, or lambda into t is equals to k. But what is this lambda? This lambda is not the maximum wavelength. This lambda max, when we write a lambda max, it does not mean maximum wavelength, it means wavelength for which the intensity is maximum. Like here, as we increase the temperature, the wavelength, the lambda max, or wavelength at which maximum intensity is there, it will shift on the shorter side. So according to Wien's, the lambda max is inversely proportional to temperature. So if an object is high, like example, if you have a black body at a high temperature, then it will emit out a shorter wavelength as compared to a black body at a lower temperature. And keep in mind, the SI unit of temperature is Kelvin. So when you use this formula, you have to substitute this in Kelvin. The value of this Wien's constant, the proportionality constant, the K, is 0.0029. So we can also say, or 2.9 exponent minus 3. So we can also say that lambda max, but when I say lambda max, it does not mean maximum wavelength, because this is the maximum wavelength. Lambda max means wavelength for which intensity is maximum. So lambda max multiplied by t is equals to 2.9 into 10 to the power minus 3. Because 0.0029 or 2.9 into 10 to the power minus 3, that will always be the value of the constant of the black body. So we consider the stars as a perfect black body. So using this, like how we are able to say that the sun temperature, the specific temperature of the sun, the surface temperature of the sun, or different stars. So how we are able to predict, how we are able to say this temperature without probing directly, like we are not sending an instrument to that star, or even for sun. So we are just recording information, the data of the graph which we obtain from the intensity and the wavelength graph. So we focus, like a radio telescope is there. So a radio telescope focus on a specific star. For example, we focus on sun, and we are getting this graph. So using this graph, like intensity, how much energy coming on unit area in 1 second, and the wavelength. So using a maximum value of the intensity, we work out the maximum wavelength, lambda max. But lambda max means that it is a wavelength for which the intensity is maximum. And using lambda max, because we know according to Wien's law, lambda max into temperature is equals to 2.9 into 10 to the power minus 3. So we know the lambda max from the graph, we know the constant, so we can find the temperature of that star in Kelvin. Is it clear? The Wien's law? So this temperature of the sun, like how we are able to say it is approximately 6,000 Kelvin. So we have this data information that the radiations which are emitted out from the sun, it is emitting out different wavelengths, but the majority of the wavelengths are in a green and yellow region, the peak wavelength, and using that peak wavelength we identify lambda max, and lambda max 2.9 exponent minus 3 divided by lambda max. So we'll work out the temperature of the sun, which is approximately 6,000 Kelvin. That's a surface temperature. The temperature of the core, definitely there's a nuclear fusion inside, so it will be much higher than at the surface. Then the second law which relate this black body, that is called a Stephen Boltzmann law. According to this Stephen Boltzmann law, that the luminosity means power. When in astrophysics, when we use instead of using a term power, we use the term luminosity. So according to Stephen Boltzmann law, luminosity is directly proportional to fourth power of temperature in Kelvin. So this is a relation, like example, if we have two black bodies, even two stars, because we are applying the black body, this is actually for black body, but they consider star as also a black body and apply these laws. So according to Stephen Boltzmann law, that luminosity is directly proportional to the fourth power of temperature. So what does it mean? Example, if one of them is about 2000 Kelvin, another one is 4000 Kelvin, the object, two objects of same size, so 4000 Kelvin. So when the temperature is double, what happened to luminosity? It will increase by fourth power. So 2 multiplied by 2, 4 into 8 into 16. So what happened to luminosity if the temperature is double? That it will become 16 times the original value. But the issue, another thing is there, that for example, if you have two objects of at same temperature, so they should give the same, like example, this one is at 2000 Kelvin, object A, and object B is also 2000 Kelvin. So if two objects have the same temperature but they have different size, so it means they should have, according to this formula, Stephen and Boltzmann, they should give the same luminosity, but practically they give different power. They have different power output. The object which is larger in size having a higher power output. than compared to object is smaller in size. So it also states that luminosity is also proportional to surface area. Larger surface area, higher luminosity as compared to smaller surface area. So when we combine these two relation, so we can say luminosity is proportional to surface area and temperature is to power 4. But again, when we replace the proportionality sign, we should replace with equal to and constant. So L is equals to sigma, that is called a Stephen Boltzmann constant. Surface area, how to find a surface area? Because these are spheres, the stars. So what is the area of the sphere? Area of the sphere is 4 pi r square, the surface area. So this is a sigma, a Greek alphabet, which is a Stephen Boltzmann constant. Surface area will be 4 pi r square and t raised to power 4. So this is a formula which we can also use to work out the size of the star. Like we normally categorize the star, we say we have a red giant, blue giant, super giants, or neutron stars are there, dwarfs are there. So how we are able to predict, how we are able to say, like categorize these stars, we can categorize them in terms of temperature as well as in terms of size. And how we can work out the size? So using a blackboard, like focusing, we focus on one star, we plot these, collect the result, plot a graph for intensity and wavelength, and find the maximum wavelength, like the wavelength at which the intensity is maximum. Using that maximum wavelength, we'll find the temperature, and using a temperature and the luminosity can be calculated, like how much power I receive on, if I know the intensity, like this one is intensity, how we relate intensity with the luminosity. So intensity is equals to power on unit area. If you remember this, you were studying this formula in AS, the last topic, which was about light, radiation flux or intensity. So that is power per unit area. And here in astrophysics, for power we call luminosity. So we can say intensity is luminosity divided by area. So using this, we can identify, like find the luminosity, and using a luminosity and the temperature, we can find the size of the star. Is it clear? How we can find the size of the star, or how we can relate the size with temperature and the luminosity? Then how to find the size of the star? How we can use, first we'll have the result, because like example, say I'm finding a size of the sun. So we will collect the information, the intensity, the radiation, will collect the data of the intensity which we receive on a unit area. So intensity which we receive on a unit area, we can find the luminosity as well. And we will sketch the result of intensity and the wavelength using a maximum intensity, like using a graph of intensity and wavelength. Intensity at which the wavelength is maximum, we will use that maximum wavelength and use a Wien's law to find the temperature of the star. After knowing the temperature, so we have the temperature now, we have the luminosity. This is a Stephen Boltzmann constant, a fixed value. So we can just find the radius or the size of the star. Is it clear? Then finding the distance between a distance of the planets, stars, and galaxies. So we can use different laws. We can have a Kepler law. Kepler first law is there, second law is there, third law is there. We can use Hubble's law. We can use a standard candle model. We can use a trigonometric parallax. So first one, how we can use a Kepler law. According to Kepler's first law, what is the statement of the Kepler first law? Kepler first law state that every planet orbit the sun in an ellipse with the sun at one focus of the ellipse. Maybe in mathematics you have studied ellipse, the shape. So the first law state that every planet orbit the sun and the sun is in an ellipse, and sun is one of the focus of the ellipse. So what does it mean? It means, like example, so this is a sun, and the planets are moving in an ellipse. So according to the Kepler first law, like because this is an ellipse, so there will be one focus here. Focus, to understand simple, like example, if I have a curved surface and the parallel light rays are there. So if I have a curved surface and the parallel light rays, so these parallel light rays will converge at one point, and that point, what we call that as a focus. So same thing, according to Kepler's first law, that this ellipse will have two focus. One of the focus will be the sun. Like when it is here, the sun is the focus. When other way around, this will be a F2. But one of the focus is the sun. That is one thing. Kepler first law. Then Kepler second law is actually like extension of the first law. That what is the Kepler's second law? It states that the planet sweeps out equal area in equal time in its orbit around the sun. So the planets will basically sweeps the equal area in equal time around the sun. So what does it mean? Like example, say the planet, if we are example talking about Earth. So example, in the month of the May, This is a position of the planet. And after, after a month like June, this is a new position of the planet. So when we compare the area which is swept or area covered within a month, so that this is the total area according to this focus. This is a total area which is covered. Same thing, say example, if it is in November at this position, in winter, like this is a position November, and this will be in December after a month. So when we calculate this area related to the focus as the sun, so it will sweep out the same area. Means these two will have the same areas. The area of this part will be equal to area of the other part within a month. This part is having a greater height, smaller width. This is having a greater width, smaller height, but the total areas of the two positions. So the Kepler's second law simply state like planet sweeps out the equal areas in equal times in its orbit around the sun. So using this, and we know about the Kepler third law, in which we discussed that the time period square is proportional to the distance r cube. And about the third law, we know that we already derived that t square is proportional to r cube, because both have the same areas. If I say here, or when I just find a relation, like example, t square divided by r cube will be equal to constant. So we can say t1 square over r cube, r1 square is equals to t2 square over r2 cube. And then we simplify this formula. How we can simplify the formula? That t1 over t2 is equals to r1 over r2. So t1 over t2 square is equals to r1 over r2 cube. Is it clear? Where t is the period of the orbit and r is the distance from the sun. And 1 and 2 are showing the two orbiting bodies. Like it's a comparison, like two different orbiting bodies are there. So using this relation, we can find or use a formula. Like if I know the time period of the earth, if I know the time period of the earth, and I want to find the time taken by Mars, so I can use this relation to compare them. Is it clear? Then another method is there which is called a standard candle. According to standard candle model, what we assume that the luminosity is constant or the power is constant. So we assume that the luminosity or the power radiated is constant. Like example, if this is a star and we want to find the distance between the star and the earth is smaller compared to, like, even the sun-like star, it's too big compared to that of earth. So if we say the distance between the star and the earth is d, and this star is emitting out having a constant luminosity or power, so we can use the formula that intensity is equals to power per unit area, or radiation flux is power per unit area. But when we calculate area, like because this star is emitting out, like the distance between earth and the star is d, but there are so many points which are at a distance d away from this star. So this star is emitting out radiation in all the direction, and the same distance d will be there. So when we join all these points, what it will become? It will become a sphere. With the source, the center will be the star. These all distances are same. It does not appear to be, but it should be same, which shows that the relation, because we want to drive. So intensity can only be calculated how much power is coming on a unit area. And we assume in a standard candle, we assume that the star, assuming that the radiation or the power which is emitted out from the star is constant. So what it will make? It will make a perfect sphere. So intensity will be equal to power divided by 4 pi d square. And what is d? D is the distance between earth and that star. So we can identify, we can have the intensity. How we'll get the intensity? Because we are collecting a information, like how much energy is there on unit area in 1 second. So we can collect by instrument. We can calculate the power, how much energy is there on unit area, energy coming in 1 second, that is power or luminosity. So we can find the distance between the earth and the star. So this model, this technique is known as standard candle. So astronomical objects, star with known luminosity or constant power, we call them as a standard candle, such as like the supernova or Cepheid variable. So if you want to calculate the distance, the flux of the standard candle must be measured. Like how flux means how much energy is coming on unit area, and one of the this method we can use it to find the distance between the star and the earth. Is it clear? This method, the standard candle. So the remaining trigonometric parallax, Hubble's law, Hubble, to find the distance and the types of the stars and the fate of the universe, star cycle, that we will discuss in the next session. Any question related to the class today? So I'll end the session and share this recording.